I'm Dr. Katie Hurlburt, and I'm at the NASA Johnson Space Center. I've been an engineer at NASA for nearly 30 years, and I'm here today to present to you on the technology roadmaps that NASA has created to help drive our decisions in technologies that we choose to develop for future missions. Today, we're talking about, or have a presentation from the roadmaps that were developed originally back in 2012, but recently NASA has updated those roadmaps. And right here on this chart, we have a link that you can see takes you to the most recent versions of those roadmaps. And if you scroll down, you can see that all of the roadmaps cover a variety of areas, all technologies needed for our future missions. So we have quite a few roadmaps. Also, TA0, which is shown right here, talks about technologies that are cross-cutting across various technical areas. But we have anything from propulsion, life support, nanotechnology, thermal management systems for spacecraft, etc. And this time, in 2015, we included aeronautics, which was not included in 2012. These are excellent resources for anybody looking to develop technologies that would be used on spacecraft. And it gives a broad range. It's also been reviewed by the National Research Council. This presentation I'm providing today will be updated after the National Research Council, NRC, has reviewed our most recent roadmap and basically provided any updates that they would recommend. You can also Google NASA technology roadmaps, and that should lead you to the same link and information I'm providing to you today. On this slide, you can also see that this is a graphic that shows all of those roadmaps and where they might fit into future missions and development programs. Today we're going to focus on TA06, which is the Human Health, Life Support, and Habitation Systems Roadmap. And I was the chair for this roadmap that was developed in 2012, and I was lucky enough to be the co-chair with Dr. Mark Kliss of the Ames Research Center for the update that's just recently come out in 2015. So today, an overview of what I'm going to talk about is the roadmap and what it includes. Also, the breakdown structure of the technologies, how they're organized inside of the roadmap. The defined technology readiness levels for the technologies that we'll see. Overview and highlights of particular examples of technology that NASA continues to work on for future missions. Then we'll summarize, and there's also additional appendices if you would like more information and request this presentation from the vendor. So an overview of what the roadmaps contain. For human health, life support, and habitation systems, the primary purpose of developing the document was to achieve the predicted national and agency goals. And then included in there, we are looking for game-changing technologies that would basically alter how we've done space missions in the past to what we intend to do in the future, including those that would be leading to a planetary surface. And specifically, our roadmap, TA06, focused on crewed missions as opposed to robotic or autonomous missions. Some of the areas that we're looking at: environmental control and life support systems. We're going to be talking about habitation systems for the crew. We're going to talk extravehicular activity systems, which is essentially the spacesuits. We're going to talk about human health and performance for the crew. And we're going to talk about environmental monitoring and safety and emergency response. Another big topic that was updated for the 2015 version is the radiation area. So in 2012, we introduced that. What you'll find in the recently released 2015 edition is a lot more content in the radiation area. So the breakdown of how we organize the document: first of all of those other topics we discussed are broken down into subsystems below. So, as an example, the environmental control and life support system includes the air revitalization system, the water recovery management, the waste management, which includes waste generally from the mission overall, and also, and also the habitation systems we discussed that keep the crew comfortable and support them throughout the mission. The EVA systems include everything that is needed for the spacesuits. That includes the pressure garment itself, the portable life support that the crew needs to breathe, and power, avionics, and software systems that keep the suit running. The human health and performance includes the medical diagnosis and prognosis, long-duration health and how those technologies will assist the crew in being able to do long-duration missions such as to the planetary surface, behavioral health and performance issues, and human factors and performance as well. The environmental monitoring, safety, and emergency response cover things like sensors to make sure that all of the systems are operating to protect the crew, such as water. If the water is contaminated, then the crew cannot use that water for potable reasons and must process it before they are able to utilize it or drink it. Fire systems, such as the detection of fires and how you manage the fire suppression once a fire occurs. Protective clothing and breathing apparatuses, and remediation if you've had an event and you need to recover from it. Radiation is also covered more thoroughly in the 2015 edition, but in the 2012 edition, you'll find risk assessment modeling, radiation mitigation procedures, protection systems, space weather prediction for radiation events, and monitoring technologies for the radiation the crew is exposed to. This listing provides the technology readiness levels, and what that basically states is for the systems that we're developing, where are they compared to being a concept versus being able to be implemented in the space vehicle. As an example, TRL-1 is just basic scientific principles have been observed, and now you're ready to apply those principles to developing a system to employ on a space vehicle. All the way down to TRL-9, these are the systems that are currently being flown in space or have been flown in space operationally. And then somewhere in the middle, TRLs 4 through 6, those levels essentially provide most of our development activities. So they're somewhere between component subsystem validations, you're developing a benchtop system, to subsystems that have been demonstrated in a relative environment, such as in a vacuum chamber or a simulated environment for space. We're stuck on that. It won't go forward, I'm sorry. Should I press something here? There we go. So the first thing we're going to talk about is an overview and highlights for the environmental control systems and life support. And these systems maintain the environment that would be suitable for the crew to live in space and operate in space. So human beings essentially are going to go out farther in space beyond low Earth orbit, especially to the planetary systems. Those are very long duration missions. They will no longer have the ability to get resupply from near Earth, and they will not have the ability to do an emergency return. As an example of a game-changing technology that is needed for this and that is being pursued, waste management is critical because over time, especially long duration time, the waste can build up and the crew needs to be able to handle that safely. Another example of an enhancing technology system would be to see if you can recover oxygen from the CO2 that the crew is breathing out. And that way you don't have to have as much oxygen tanks or resupply systems. You can grab that from the CO2 that is being removed from the human environment. So I've blown up a diagram that basically shows what an environmental control system might look like. Everything on the diagram shows arrows that point back to other components of the system. The more arrows you have that point to another system, the more closed the system becomes, and the less you need to take with you as a resupply. So the issues we have here in the diagram is when we have overboard venting, you can see that for the CO2 system, or you have overboard venting for the hydrogen system. Those are consumables which are lost. So if you can find a way to remove from the CO2 the oxygen component and reuse that in the system, that means you have less makeup supply or less consumables you have to take with you on the space mission. One example of that is we're pursuing removal of carbon dioxide from the cabin or the suits themselves to be reused. And in this case, you can see over here in the pictorial diagram, there are technologies and devices that will facilitate the CO2 capture, obtaining that gas, and breaking it down so that you can take the oxygen component out of that gas and potentially reuse that in the cabin environment or in the spacesuit. So in this case, the key becomes you need it to be very small or compact, you need to be reliable, that can operate for long periods of time without any servicing or maintenance. And you need it to be energy efficient. And you need the materials to be able to be reused over and over again without replacement. On the next slide, we see an example of recovery of water systems from wastewater. In this case, wastewater and product water has to be stabilized. It has to be maintained safely away from the crew. And then you have to have compact and reliable systems that allow you to clean that water and reuse that water. So recovery from water, as an example, is very challenging. If you were to do laundry on a long-term space mission, that water that is used for laundering must be processed before the crew can reuse it again. Also, if you're recovering water from various components of the system, a lot of times the contamination in the water is turned into a brine. And that brine then becomes, again, a consumable or a waste. So a big effort is going on right now to be able to process brines, to be able to get water again out of the brine and be able to close that loop and reuse that water. Again, on the next slide, what we see is this is the water cycle that you see in space. So you start on the right-hand side with potable water that the crew can use for various needs. That water is supplied to mobility items, such as this is meant to be a rover. It's a little strange design there, but it's meant to be a rover. And also, it can be cleaned up and used by the crew for various needs, cooking, cleaning, drinking, whatever is required. And then the crew itself, there's wastewater regenerated, and also the mobility items end up having wastewater that is not utilized. So when basically the dirty water is collected into storage, you have to have processing systems. A lot of times there are multiple steps. You have a primary processing, and then you have other processing. Again, out of the primary processing, a lot of the contaminants are put into a brine, concentrated. You'd like to be able to get that water recovery and, again, go through the post-processing to bring as much of that water back to the potable water storage for reuse again. Anything you lose, you have to make up by bringing additional tanks or bringing systems, again, that can process other consumables into usable water. Another example technology is waste collection and stabilization. This becomes much more difficult on a long duration mission because of the quantity of waste that you receive. The solid waste, trash, and even fecal waste from the crew has to be managed safely and should be processed for further use, if possible, or reuse. A great example of this was in the recent movie, The Martian. It showed you that he utilized what I believe was freeze-dried feces to basically rehydrate and put into his plants. And so that was a great example of using something, a waste, that essentially would not be usable otherwise, but producing something else that he needed on the mission. Another area that we're looking at is habitation. A great example of the needs of the crew here is the clothing supply. Currently, we don't have effective laundering. Sorry, let me get back there. We don't have effective laundering capabilities, especially for long duration missions. So the clothes, we're trying to find fabrics and techniques where the clothes can be worn for extended durations without those needs, and make sure they're palatable to the crew so that there's no odor, degradation of the clothing itself. Trying to make it so those clothes can be stretched out. Again, less consumables, less water consumption, and being able to stretch that out for long duration. The next area in the roadmap document is the spacesuits, and in this case, that includes launch, entry, and abort suits as well. So advancements in this area, of course, needed for crew safety, especially in the planetary environment where you have other things that we haven't dealt with before, such as dust. The systems have to be affordable to be built and also sized for a variety of crew sizes, crew physiology, and also they have to be sustained without any kind of logistical support from near Earth. So an example again of game-changing for the new suits is advanced materials that don't currently exist. Especially where it comes to planetary environments, dust and radiation become an issue. Also, advancements in the architecture and design of the suit itself. You can see a great example here, an artist concept of this suit not only provides sustainability for the crew member inside, it provides mobility away from the space vehicle. One of the advanced technologies that's being actively pursued is for thermal control of the suit. Even though it would seem that you're in the cold of space, when you're inside the suit and you're working, you sweat a lot and you create a lot of heat. The suit systems themselves also create a lot of heat. Your avionics systems and power systems also put out heat, just like your computer does at your desk. So when you have that heat, you have to get rid of it from the suit. So this technology, the suit water membrane evaporator, actually utilizes water, and the heat goes into that water and then creates the gaseous form of the water, and that gets vented out into the vacuum of space, thus rejecting heat from the system. This system is actually being tested right now in a vacuum chamber on Earth for the first time with humans to be put into advanced spacesuits. We talked also about spacesuit materials and advancing those. It's of interest to know that spacesuits are not made of one material. They're actually made of many, many layers of material that have various purposes. So advancing these suits requires us to add other layers that would protect from other things such as radiation, dust, perhaps a layer that would repel dust or be able to be managing the dust, such as putting it into certain channels to keep it away from other parts of the suit. So there are lots of advancements in the materials themselves that can lead to these layups and fabrication of that future suit. The next major section of the roadmap addresses the environmental monitoring, safety, and emergency response. In this case, these are technologies that are needed to ensure that the crew stays healthy, and that also addresses some of the safety concerns. So monitoring, prevention, safety systems are all geared in this section to critical hazards such as contamination or fires. Now remediation, should an event occur, also is important. It's possible, especially on long duration missions, that you could have an off-nominal event, and then the crew is on their own to handle that event and recover the spacecraft. An example of a game-changing technology that we're looking for is a standalone water quality measurement system, or total organic carbon monitoring, that allows us to make sure that the water that the crew is consuming is of high quality and will not make them ill or basically provide other issues in their functioning. Another example is the post-fire remediation, which right now, if there is a fire, we don't really have a recovery plan other than to bring the vehicle back and service the vehicle here on Earth. And you can see by the flame diagrams here, this is in normal gravity. Actually, fire reacts very differently in zero gravity, and it's certain to react very differently in planetary gravity. In that case, we also need to understand what the fire will do to the space vehicle under those conditions. We're also looking for sensors to be able to real-time monitor air and water and other critical parameters. And right now, we don't have the ability to do real-time monitoring of those things in the space vehicles. So samples are taken and monitored non-real time, and sometimes those samples have to be transported all the way back to Earth, such as water samples, to get a full analysis. So we're looking for very advanced systems that can be modified from what we do on the planet and take it into space or into the planetary environment, such as spectrometers. We talked about fire suppression systems, and this is very critical. Right now, the systems that we have on orbit are not gaseous-based. They are now coming up with technologies, and soon to fly, that are testing carbon dioxide and other basically gaseous forms of fire suppression. We can also see over here, this is a special aircraft. It is available to the public. It is Zero G Corp, and they offer zero gravity research opportunities. So some of the things we talked about before where the flame is dependent on the gravity level, you could test that in a Zero G Corp condition for both planetary and zero gravity to get an understanding of how the fire will react and better design the fire suppression system. Now on to human health and performance. Basically, this focuses on technologies to maintain the health of the crew and support their performance throughout their mission. It's a significant area of challenge, especially as you go into farther and farther missions away from Earth and also long duration. I think the movie The Martian shows that very well. Very far away, no help, and communication is also significantly delayed. The crew is expected to operate much more autonomously, And you have other considerations that have not been as important for short duration missions in orbit, such as the psychological health of the crew members. An example of a game-changing technology is virtual reality. If the crew members are basically gone for a long period of time, virtual reality could be used for training purposes, could also be used for entertainment and other needs. Another example is advanced human screening, where in the selection of the crew, now that we are understanding genetics more effectively, you might be able to select your crewmates based on the risk that they have for certain conditions, malignancies, exposure to radiation, and other things that they're predisposed to. So you may be able to optimally select crew members for a particular type of mission. Another advanced technology that we may need on future missions is in-flight medical evaluation. And this would mean basically near real-time evaluation of a crew member's condition that we don't currently have. The technologies, as an example, that we have on Earth, we don't operate in zero gravity as yet. One example is the ultrasound imaging. If there is a serious issue with a crew member, before you would take medical action, perhaps even surgery, you would want to understand the condition internally. Ultrasounds are being developed and going to be tested on the International Space Station soon. The recommended timeline suggests here that they would be tested by 2017, and we are on target to test some of these diagnostic instruments soon. Another advanced technology that we're looking at is non-pharmaceutical treatments, meaning no drugs, for sensory motor flight disorders. And this would have anything to do with your neurological condition. Balance is a great one to look at. Both in zero-G and in planetary environments, you could have neurosensory disorders related to the gravity change. One of the things I wanted to highlight is down here on the lower left. This is a short radius centrifuge, and it's designed to spin two crew members at the same time. When we look at that more closely, we can see up here the centrifuge, and this is designed to basically provide G-loading from the head to the feet, which is very different than what you see normally in centrifuge, either on the ground test facilities or in a aircraft, which is basically a seated position. So in designing a centrifuge and determining what would basically assist the crew member, there's design parameters that have to be considered. So in your space vehicle itself, we've seen a lot of movies that show the entire vehicle spinning. And that is a solution, but if you spin the vehicle, you still have to know what gravity level, what spin rate, and other parameters to determine what would be optimal for the crew. If you choose not to spin the entire vehicle, you can still provide spinning facilities like a chair. But then again, you have the same issues of how long do you spin, what gravity level do you spin at, what time of day do you spin, and what activities do you do while you're spinning, such as exercise. The other issue is on planetary missions. If you're traveling very far away, you've been in zero gravity for an extended period of time. When you go to the planetary surface, you're going to get partial gravity, such as Mars, which is about 3/8 of the gravity of Earth. In that case, you're going to go from whatever you had in zero gravity to now having low gravity. So, do you have enough on board as far as your muscle and your neurosensory to establish yourself and effectively operate in low gravity? The answer is no. Then again, you have to come up with a prescription or some solution that you can implement to make sure the crew can perform their functions in the gravitary environment. We also need advanced displays and controls in the future. Wearable technology has been looked at recently, and in fact, a great example of that is Google Glass. And you can see these are earlier versions, and so the advancement in technology, even from the 2012 version of the roadmap to now, has changed substantially. But in the development of these displays and controls, again, going into zero gravity or planetary gravity, your systems operate differently. So the eye operates differently. Your physiology is completely different. So you have to test these systems in zero gravity or on planetary gravity to make sure that they're still functional with the physiology of the crew member. The International Space Station offers that opportunity to do some of that testing. Another advancement we need is in cameras and in communication systems. A great near-term example of what we had from 2012 to what we have now is the development of the GoPro camera. That's a great example of the cameras that we had even 5 to 10 years ago. You can see the substantial advancements. Those systems can now be incorporated into future space missions effectively. Another example in the human health and performance area is biosentinels. These are suites of nanosatellite platforms, test platforms, to carry out experiments that are unmanned in orbit. And we know that biological systems such as cells and microbes are affected by the gravity change. So these allow you to take those systems into orbit and find out the mutations or the changes that happen in the cells or the microbes themselves. Technologies under consideration then related to this type of work are drug dose dependencies. So if you have changes in the environment of space, you might then be able to prescribe medications that would be more effective in that particular environment. Radiation is the last area of this particular roadmap, and again, it's been enhanced in 2015. But even in 2012, it was identified as a critical area to develop technologies. We needed to quantify the radiation health and performance risks for our crew and for our vehicle. We need to monitor space radiation and the exposure that the crew has to it. And we need to develop mitigations and countermeasures and minimize the overall exposure to the crew. We lack significant data in this area, which is why it's emphasized in the 2015 versions of the roadmaps. We also need to effectively design integrated radiation protection systems. And you can see on the right, some of the concepts include developing walls that are tanks. As an example, water is a good moderator of radiation. So if you were to store your water in some kind of structure in the vehicle, having those water tanks provides radiation protection for the crew. Another area is radiation mitigation and biological countermeasures. What can we do to protect the crew from chronic galactic cosmic radiation, which is basically a driver in their health, and also protect them in case of an off-nominal event, such as a solar particle event? Part of that is to determine the space weather. Similar to what we do on Earth, we want to be able to avoid the solar particle events, or at least predict them, and make sure the crew can get to a protected area or some alternative to that. Space weather is not reliable at this time, and we'll talk about how can that be improved in a couple slides. An example of the technologies under radiation is we need active radiation dosimetry of each crew member. Each crew member, depending on where they're located and their activities, get different doses that need to be monitored actively and handled individually. In this case, we have dosimetry technology, but it needs to be miniaturized, radiation hardened, and it needs to be very efficient and real-time monitoring. On the next slide is space weather again. Similar to what we do on Earth for hurricane tracking, we need to be able to do that in space for radiation and also for solar particle events. In this case, if you have a solar particle event, what you want to do is be able to say how long will it last, what is the general direction and area that it will cover, and then you can basically come up with a plan such as we do for a hurricane, where we either evacuate, protect our homes, and other mitigations. In summary, the roadmap provides a lot of technology listings that are approved by the NRC in the areas of human health, life support, and habitation that will be needed for future missions. Thanks for joining me today.